Hello, my name is Tomasz Kucner. I'm with Örebro University from Sweden. I am here to present our work on robust frequency-based structure extraction. In our work, we have developed a method for extracting and assessing the structure of maps of human-made environments using the Fourier transform. In the figure on the right, we can see an application example where information about the environment structure is used to remove clutter automatically from the map. Autonomous mobile robots are increasingly being deployed in shared human-made environments, such as warehouses, factories, hospitals, as well as airports, train stations, and even our own homes. However, the share of robot deployments is vanishingly small compared to the size of these markets as a whole. One severe barrier for robot deployment is the cost and engineering labor required for map creation and validation, especially in settings where high precision and repeatability are required. Human-made environments are well structured and mostly consist of straight walls. That applies to domestic environments as well as to the industrial ones. Many robots can build and use a map of their environment to navigate and localize via SLAM. However, even the state-of-the-art SLAM methods can produce maps with misaligned elements and artifacts, as we can see here. Even though that the map on the left looks correct at first glance, contains multiple wall misalignments of varying sizes, while the map on the right contains artifacts caused by moving entities in the environment. Both the errors and the artifacts can negatively affect the quality of the robot's navigation and hinder the semantic understanding of the map. Moreover, even a nominally correct map on occasions needs to be manually cleaned of clutter before it is used in production. The best example being room segmentation, where the presence of objects not belonging to the building level structure in the map will lead to oversegmentation. One of the ways to tackle the problem of structure extraction from a robotic map is to gain access to ground truth representation of the environment and align it with the robotic map, thus gaining a reference which can be used for map refinement and decluttering. Although such approaches yield positive results, they assume access to the ground truth map. Such a requirement cannot always be fulfilled. Thus, in our work, we attempt to answer the question how to perform a reference-free structure extraction. To tackle this issue, we propose robust frequency-based structure extraction, in short, ROSE, a method for extracting building-level structure from cluttered and distorted maps using Fourier transform. Here we can see rows performing the clutter removal. The grayscale map represents the cluttered input map and the magenta map represents the map after filtering. We can see that depending on the set filtering threshold, different amount of pixels are being retained. The video shows that the method favors pixels belonging to the building level structure, walls, and discard pixels not belonging to them. The higher the threshold, the fewer pixels not aligned with the wall directions are retained. In the following part of the talk, we will discuss how ROSE extracts building level structure from cluttered maps with mostly straight walls using Fourier transform, how information about structure allows removing clutter from maps. Finally, we will also present how the map filtering can improve the performance of room segmentation. ROSE operate on 2D occupancy map. Here we can see an example input map containing walls aligned along multiple dominant directions, as well as some clutter. The first step is to compute 2D Fourier transform of the input occupancy map. Here we can see a resulting frequency image of the map. We can see that there are lines which are corresponding with the dominant directions of the walls in the map. Working with such representation might not always be convenient. Thus, to simplify the following step, we unfold the frequency spectrum. That means we convert the frequency image from Cartesian to polar coordinate frame. We assume that the origin of the coordinate frame is the center of the frequency image. Then we plot the frequency spectrum as shown in the figure on the right, where the horizontal axis is the direction, while the vertical axis is the cumulative amplitude of the pixels in the given direction. Such a modified representation allows easy identification of directions with the highest cumulative amplitude, which indicates that the walls in the environment are aligned along them. In the plot, we can see 10 pairs of peaks that correspond to 10 directions of walls in the map. This information will allow us to build a bandpass filter, allowing to retain only the parts of the spectrum that correspond to walls in the environment. The filter is built by masking all the pixels in the folded frequency image that does not correspond to the directions of the detected peaks. Here we can see the result of filtering the map in frequency spectrum. On the left, we can see the input map. On the right, we can see how much each pixel contributes to the global structure of the environment, as identified in the previous step. The score of each pixel of the map is computed as amplitude from the inverse Fourier transform of the filtered frequency spectrum. The brighter colors correspond to the pixel well contributing to the structure, while the darker ones correspond to the pixels not corresponding to the structure. Now, through thresholding, we can decide which points should be retained in the final map and which should be discarded as noise. Here, the green pixels will remain in the map. We can see that parts of the map that does not align with the main walls in the map are not marked green, even though that they might be aligned in the dominant direction. Such behavior shows that not only random clutter will be removed, but also the elements of the environment that are not crucial for the structure of the environment. Now, let us discuss the practical implications of the map filtering. We'll focus on the problem of room segmentation. The process of room segmentation is a way to automatically split the map into semantically meaningful regions, rooms. However, the process is sensitive to clutter and misaligned walls. Both can be falsely identified as walls and lead to oversegmentation of the environment. Thus, the filtering step, removing the clutter and misalignments, allows to mitigate their impact. Instead of assessing the complete room segmentation pipeline, we will focus on the first step, wall extraction. This step allows identifying the walls, which later on are used to split the map into the rooms. Here we can see a simple example where wall lines, long red lines, are extracted without and with filtering. We can see that the not filtered clutter is often recognized as additional walls and lead to oversegmentation. We can see that in the figure on the right, there are walls that correspond to the non-existing parts of the environment. To quantitatively assess the impact of the clutter on the wall extraction step, we have manually labeled 16 maps of indoor environments and then measured the average transformation cost to align each of the detected wall lines with and without filtering and the manually labeled ones. The transformation cost is computed as combination of the distance between the centers of the wall lines and the rotation needed to align them. Cost computed in such a way allows to capture the information not only about the erroneous detections, but also includes redundant wall line detections. In the plot on the right, we can see a comparison of the average transformation cost for 16 different maps. The green points correspond to the filtered maps, while the red ones to the unfiltered ones. The plot shows that the map filtering allows to significantly lower the transformation cost. Let us now analyze an average example of the wall extraction. As we can see in the figure on the right, the not filtered map is more susceptible to false wall detections and misalignments. In contrast, the map on the right has fewer false wall detections, as well as the wall detections are more accurate. It is also important to mention that the proposed method has its limitations. Here we can see a case where the result for the filtered and non-filtered map are not so distinct. The key reason for such a behavior is the high complexity of the environment and a large number of details, although filtering allows to lower the number of false wall detections and assures that the detected wall lines are better aligned with the real walls. So far, we have not discussed how to decide which pixel to retain in the map as part of the structure and which one should be discarded as clutter or noise. Of course, it can be done by manually deciding a suitable threshold for the map. However, such a method will be cumbersome and will require expert knowledge to perform such a selection. Instead, we propose to use a method based on B-model Gaussian mixture model. In this slide, we can see a real-world map with added artificial noise. The map has undergone the process of computing its Fourier transform, detection of the dominant directions, and scoring of the map pixels. The pixels are color-coded according to their scores here. In the next step, all pixel values are distributed on one-dimensional axis. To decide which pixels to keep and which to discard, we fit a one-dimensional B-model Gaussian mixture model to the distribution of pixel values. The threshold is set for the value for which the two Gaussians intersect. All of the points with the scores above the value of the intersection will be retained, while the remainder will be discarded as noise. In order to assess how well the automatic threshold detection for clutter filtering works, we have selected 6 maps from the reddish dataset and added 3 different shapes of obstacles in varying amounts and varying sizes. We have evaluated it as a classification problem, thus we have computed the precision and recall for each map. The precision plots are in red and recall are in green. The key observation is that the type of the environment will affect the result. The more complex and unstructured an environment, the worse the precision score. The second conclusion is that the key factors affecting the classification are size and amount of obstacles. In both cases, we can see that increased number and size of obstacles causes a drop in the precision, although the recall remains fairly unchanged. Finally, we can use the information about the amount of the structure in the map to assess the overall quality of the map. In the presented example, we can see 2 maps of this same environment. On the left, the map is heavily distorted, while the map on the right is well registered. On the right side of each map, we can see the plot representing the cumulative score for each direction in the map. Furthermore, on each plot, an average signal value and average peak value are marked. As we can see, a small ratio signal to peak value indicates a relatively well-structured, uncluttered map. Before the end, let us briefly summarize the content of this work. In this presentation, we have presented rows, a simple but efficient method for extracting building level structure from 2D grid maps. We have presented use case where clutter was automatically removed using information obtained via rows. We also presented how rows can positively affect wall detection in real-world maps. Thank you very much for your attention. If you are interested in applying our work, please visit our GitHub repository.